Greetings, students, and welcome to the first episode of a two-video series on section 4.9, which is dealing with the solution of systems of linear differential equations by the technique of elimination. Uh, we're going to begin by taking a look at an exercise number 7 from section 4.9. And as you see here on the screen, kind of circled in the black bubble or blob is a pair of equations, d squared x dt squared minus 4y equals e to the t, and d squared y dt squared minus 4x equals minus e to the t. So these are two second order differential equations, and the thing to notice about them is that they both they tell us how two functions, x and y, relate to each other and to an independent variable that we're calling t. So t is the independent variable, and x and y are both functions of t. And so what we're trying to find here is we've got these two equations, two differential equations. We're trying to find functions x and y that both satisfy the two equations. Now, to help do this, some notation is helpful. When we talk about the derivative of y with respect to t, and here I'm going to annotate this a little bit here. When we talk about the derivative of y with respect to t, we could write dy dt, but another option that we have for that is we could use what we call differential operator notation. In place of dy dt, we could just write capital Dy, and that stands for the derivative, the first derivative of y with respect to t. So we're leaving off the variable that we're differentiating with respect to. Similarly, if we wanted to talk about a second derivative, d squared y dt squared, in differential operator notation, we could refer to that as d squared y. So just kind of a shorthand notation there, but it will help to make our equation a little bit simpler to write. With that notation, the first equation becomes d squared of x minus 4y equals e to the t, and the second equation becomes d squared y minus 4x equals minus e to the t. And so those are our two equations with two unknown functions. And we want to find out what those functions are. So just as solving a system of equations with two unknown values, we can try to do some elimination here. And how we're going to pull off the elimination here is by manipulating both the first and the second equations by doing things to them. Now, the first equation, the one involving the second derivative of x, what I've chosen to do here is to take two derivatives of that equation with respect to t. Now, another way of saying that, to take two derivatives, would be to apply the d squared operator to both sides of that equation. So when we apply d squared to each of the pieces in the first equation, well, if you take the second derivative of the second derivative, you're going to get the fourth derivative, which we would call d4 of x. If we apply the second derivative to minus 4y, that just gives us minus 4 times the second derivative of y, using the constant multiple rule. And on the right-hand side, when we take the second derivative of e to the t, that's just going to be e to the t. So we've ended up with the fourth derivative of x minus 4 times the second derivative of y equals e to the t. We got that by taking two successive derivatives of the first equation. Now, why do that? Well, the reason for doing that is to set things up so that we can do an elimination. And here we're going to do an elimination of the y function. Now, in the first equation, we now have a piece of it that says minus 4 times the second derivative of y. Notice that the second equation has initially an expression that has the second derivative of y. So what I'm going to do is I'm going to multiply the second equation through by 4. So when we multiply the first term of the second equation, we'll get 4 times the second derivative of y. When we multiply the second term, we'll have minus 16 times x. And on the right-hand side, we'll have minus 4 times e to the t. So now we have these two equations with, again, the two unknown functions. But now these two modified equations, notice they have the property that the first one has minus 4 times the second derivative of y, and the first one has plus 4 times the second derivative of y. So what that means is if we were to add those two together, we should be able to eliminate the function y entirely. So that's what we're going to do. We're going to add together this first equation and this second equation. And in doing that, what do we have? Well, the left-hand side had a fourth derivative of x and a minus 16x left over. So we have the fourth derivative of x minus 16x. And when I add together the right sides, minus 4 e to the t plus e to the t, that'll give me minus 3 e to the t. So now I have this fourth order differential equation, but the virtue now is this only has one function. We started with two equations with two functions. Now I just have one equation of fourth order with one function. And not only is this just a differential equation with one function now, but it's also a linear differential equation with constant coefficients. It's not too hard to see that if we have the fourth derivative of x minus 16 times x, that the auxiliary equation for that is going to be m to the fourth minus 16 equals 0. That in turn can be factored. And when we factor it, we're going to find out that we have, in fact, 4 roots, 2 real and 2 complex, plus 2 and minus 2, plus 2i and minus 2i. So what does that mean? That means that the homogeneous version of this equation, now bear in mind, it's a non-homogeneous equation of fourth order, but the homogeneous equation will have a complementary function that's c1 times e to the 2t plus c2 e to the minus 2t. And then coming from our pair of complex roots, since they're purely imaginary, we'll have c3 times the cosine of 2t and c4 times the sine of 2t. 4 pieces to the complementary function there for this fourth order differential equation. Now, that's the homogeneous version. Of course, as we said before, we recall that this is non-homogeneous. The right-hand side has minus 3 times e to the t. So we're going to try a solution of the form a e to the t. For the particular solution, when we substitute that into the differential equation, the fourth derivative of x minus 16 times x equals minus 3e to the t, we're going to find out that it has to be the case that a has to be a fifth. So therefore, we get a particular solution of 1/5 e to the t. So now we are halfway there because we have totally found the function x that makes both of these differential equations true. What is that function x? Well, let's go to our next screen. Bring her up here. All right. So reviewing, we now know exactly what the function x of t is. It's the sum of the complementary function and our particular solution. So c1 times e to the 2t plus c2 e to the minus 2t plus c3 cosine of 2t plus c4 sine of 2t. That's all the complementary function, plus 1/5 e to the t, which is the piece that we need to satisfy the non-homogeneity of the original equation. We know what x is. And that means we're halfway there because remember, our original goal was to find two functions, x and y, that were both functions of t. Well, to find our y, we're kind of blessed here because one of our original equations said that the second derivative of x minus 4 times y equaled e to the t. If we rearrange that equation to solve for y, we find out that 4y is equal to the second derivative of x minus e to the t. So that just means that from that original equation, that our function y has to be 1/4 of the difference between the second derivative of x and e to the t. So we just need to do some differentiation and some algebra. So we take our function x of t, and I've differentiated it twice. That produces some extra constant multipliers. And then after we take that second derivative of x, we subtract e to the t, and then we divide by 4. And when all is said and done, after we've taken our second derivative, subtracted e to the t, and divided by 4, we're going to find out that the function y ends up being c1 times e to the 2t plus c2 times e to the minus 2t. Now notice so far this is identical to what the function x was, but now it's going to deviate a little bit. Instead of having plus c3 cosine of 2t plus c4 sine of 2t, notice the minus signs here. Minus c3 times cosine of 2t minus c4 sine of 2t. And then in the end, instead of plus 1/5 e to the t, we'll end up with minus 1/5 e to the t after doing the algebra. So there we have it. We found two functions, x and y, that are both functions of the independent variable t, and they both satisfy both of the two original differential equations that we began with. We did it by the method of elimination, by doing some operations to the two differential equations that allowed us to remove one of the functions and end up with a differential equation. Here it was one of fourth order that involved only one of the functions. And from that point onward, once we got the first function, we were able to then find the second function by going back to one of the original differential equations and substituting in what we knew about one of the functions. I hope this has been instructive. Stay tuned. Coming up, we will have another example of solving a system of differential equations coming soon to a YouTube channel near you. Have a great evening.